In the last video, we talked about the fact that if I have two non-zero vectors u and v, then I can use the sign of the dot product to get some information about theta, where theta is the angle between them. So if the dot product is positive, that tells me that the angle between them is going to be smaller than pi over 2. And because the angle by definition has to be in the interval from 0 to pi, the smallest it could be is 0, so it's either going to be 0, meaning that they're parallel and point in the same direction, or acute. If the dot product is 0, the angle between them is going to be pi over 2, so that they're perpendicular to each other. And if the dot product is negative, the angle between them is bigger than pi over 2. And again, because the angle is restricted to be between 0 and pi, that means it's either an obtuse angle or it's the straight angle pi. Now, this is sort of significant, and there's a new vocabulary word that's linked to but not identical with that concept. So here's what it is. Two vectors, A and B, in n space, are orthogonal if A dotted with B is equal to 0. So the definition is that two vectors in the same space are orthogonal to each other if their dot product is 0. And of course that's 0 the number, not 0 the vector. Now sometimes people see that and they say, orthogonal means perpendicular. It does not. Be very careful. I carefully switched from u and v, which I had said were non-zero, to a and b, which I didn't say had to be non-zero. In order for the angle between vectors to be defined, the vectors have to be non-zero. But the dot product is defined, even if I have the 0 vector. And in fact, one of our properties of the dot product is that the 0 vector, dotted with anything, is always going to be the 0 number. So that says the 0 vector is orthogonal to everything. But the 0 vector isn't perpendicular to anything at all. So orthogonal doesn't mean perpendicular. Orthogonal means one of two things is the case. Either one or both of my vectors is the 0 vector, so that I can't even talk about the angle between them, or they're both non-zero and perpendicular to each other. So orthogonal does not mean perpendicular because it's not defined geometrically. It's defined algebraically. The dot product is equal to 0. Those of you who take linear algebra will study this in that class, and you'll see there's a very good reason for going with the algebraic rather than the geometric interpretation in defining orthogonality. And that gives us that 0 is orthogonal to everything, even though it's not perpendicular to anything. We'll see a little bit later on in the class that why that's a good choice here. For right now, it's just a definition. So be careful. Orthogonal often means that two vectors are perpendicular, but only if they're non-zero. If I have the 0 vector, it is orthogonal to everything, perpendicular to nothing. So they're not synonyms. All right, a little bit more vocabulary. I can define some things called direction angles, and I'm also going to define direction cosines. So alpha, and that's a Greek letter, looks like a fish, it's called alpha. This is going to be the angle between v, and I do need to say here, let's let v be a non-zero vector in n space. So alpha is the angle between v and I. Remember, that's the unit vector that points in the direction of the positive x-axis. And of course, if v is in 2 space, I'd be using the version of I that's in 2 space. If v is in 3 space, I'd be using the version of I that's in 3 space. So alpha is just the angle between a non-zero vector v and essentially the positive x-axis. Beta, that's another Greek letter there, that's going to be the angle between v and j. And of course that's also defined in either 2 space or 3 space. I just have to use the appropriate version of j that lives in whichever space v is in. gamma, which looks like a fish doing a headstand, very exciting Greek letter there. This is only defined in 3 space, and it's the angle between V and K. So these are what are called my direction angles. The direction cosines are just the cosines of these angles. Let's actually calculate alpha and beta for an arbitrary vector in 2 space. So let's let V be V1, V2, be a non-zero vector. Notice I wanted to say that the entire vector isn't 0 rather than saying that the components aren't 0, because they can't both be 0, but it's perfectly acceptable for one of them to be 0 as long as they aren't both. Okay. So the entire vector is not 0. V is the vector V1, V2. Okay. Now if I wanted to calculate cosine of alpha, okay, we said that's the angle between V and alpha is the angle between V and I. So cosine of that, using this nifty formula that we have now, that cosine of theta, where theta is the angle, I'll just say between A and B, is A dotted with B over the magnitude of A, magnitude of B. So we spent some time proving this in the last couple of videos. So cosine of alpha, now instead of A and B, I'm working with V and I. So that's going to be V dotted with I divided by the magnitude of V times the magnitude of I. But I can work this out fairly nicely, because that's just going to be V1, V2 dotted with 1, 0 over the magnitude of V, which if I wanted to I could write out as a square root. I'm actually just going to keep that there. But the magnitude of I know is just 1, because that's a unit vector. And when I work out this dot product, I'm just going to get V1, because the first components multiply to V1, the second components multiply to 0, so that drops out. So I'm just getting V1 over the magnitude of V. So that's cosine of alpha. Of course, that means that alpha then is inverse cosine of V1 over the magnitude of V. So that's my direction angle, that's my direction cosine. If I work out cosine of beta, that's going to be V dotted with J over the magnitude of V times the magnitude of J. And again, that's just V1, V2. This time we're dotting with 0, 1, and it's over the magnitude of V times the magnitude of J is just 1, because that's a unit vector. Now this time 0 kills off the first component, so I just get V2 over the magnitude of V. Turns out, if I calculate my direction cosines for alpha and beta in 3 space, I get exactly the same result. And if I calculated cosine of gamma, it would just be V3, the third component of V. Obviously, that would be a different V. That would be a V in 3 space. But it would just be V3 over the magnitude of V. Kind of a neat thing. We won't spend a lot of time working with these things, but they are defined in your textbook, and I think there are a couple of questions about them. So it's good to know what's meant by these things. Notice one thing that's very interesting is that if I look at V hat, that would be V normalized. Remember, that's defined to be, if V is non-zero, to be V scaled by the reciprocal of its magnitude. Well, that would end up being V1 over the magnitude of V, comma V2 over the magnitude of V, working with this same vector V in 2 space. Oh my goodness, this is very cool. That's cosine of alpha, cosine of beta. So the direction cosines are actually the components of the normalized vector. This applies as long as V is a non-zero vector, so that these direction angles are well defined. Obviously, if V is the 0 vector, it doesn't make an angle with anything, and we don't talk about the direction angles for the 0 vector. They don't exist.